Bismillahirrahmanirrahim. Today, in the series of lecture of IC engine, we will be covering first part of chapter 3, and the chapter 3 is engine cycles. We have talked about engine cycles very briefly in chapter 2. Now we will study in detail regarding the engine cycles in this chapter. Now, the air standard cycle. The cycle experienced in a cylinder of an internal combustion engine is very complex or a difficult system to analyze, as it is an open cycle with changing composition due to following reasons. Number one, first air in CI engine, the compression ignition engines, or air mixed with fuel in SI engine, the spark ignition engine, is ingested and mixed with the slight amount of exhaust residue remaining from the previous cycle. So the air which we are injecting inside the combustion chamber or the air fuel mixture which we are freshly inducing inside the combustion chamber is mixed with the exhaust residue of the previous cycle. So this mixture is then compressed and combusted, changing the composition to exhaust products consisting largely of carbon dioxide, H2O, and N2, with many other lesser components. After an expansion process, the exhaust valve is opened and this gas mixture is expelled to the surrounding. To make the analysis of the engine cycle much more manageable, the rear cycle is approximated with an ideal air standard cycle. So which differ from the actual by the following manners. The gas mixture in the cylinder is treated as air, an ideal gas with constant specific heats for the entire cycle, whereas in real, it is not like this. But for the ideal air standard cycle, we take this as assumption, and property values of the air are used in the analysis. The real open cycle is changed into a closed cycle. So we are changing the open cycle with a closed cycle by assuming that the gases being exhausted are fed back into the intake system because we are assuming it's a closed cycle system, not an open cycle system. The combustion process is replaced with heat addition terms Q in of equal energy value. Air alone cannot combust. Remember this thing. An open exhaust process, which carries a large amount of enthalpy out of the system, is replaced with a closed system heat rejection process Q out of equal energy value. So we are introducing two different terms, heat addition Q in and heat rejection Q out. Now, actual engine processes are approximated with ideal processes. The almost constant pressure intake and exhaust strokes are assumed to be at constant pressure. Now we are assuming that the intake and the exhaust strokes are at constant pressure. Compression strokes and expansion strokes are approximated by isentropic process. So we are taking these assumptions for compression and expansion strokes that they are happening at isentropic processes. The combustion process is idealized by a constant volume process in spark ignition cycles, a constant pressure process in CI compression ignition cycles, or combination of both in dual cycle. Now, exhaust blowdown is approximated by a constant volume process where in actual it is not like this, but for the approximation purpose, we are taking the exhaust blowdown is approximated by a constant volume process. All processes are considered reversible. So all processes are considered reversible. So few thermodynamics terms are used. Let's refresh your knowledge of thermodynamics. Now, First is the enthalpy. The sum of the internal energy and the product of the pressure and volume of a thermodynamic system is known as enthalpy. It is just to brush your thermodynamic knowledge, which you have gained in the previous years. So enthalpy is the sum of the internal energy and the product of the pressure and volume of thermodynamic system. Entropy, the measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. So entropy is the measure of the system thermal energy per unit temperature that is unavailable for doing your useful work. Isothermal process. Isothermal process is thermodynamic process in which the temperature of a system remains constant. The temperature of the system remains constant. The transfer of a heat into or out of the system happens so slowly that thermal equilibrium is maintained. So there is no change in the temperature. Thermal equilibrium is maintained. Reversible process is a process whose direction can be reversed to return the system to its original state. Adiabatic process is a type of thermodynamic process which occurs without transferring heat or mass between the system and its surrounding. So it's a thermodynamic process which occurs without transferring heat or mass between the system and its surrounding. Unlike an isothermal process, an adiabatic process transfer energy to the surrounding only as work. Isentropic process is an idealized thermodynamic process that is both adiabatic and reversible. The work transfer of a system are frictionless and there is no transfer of heat or matter. Such an idealized process is useful in engineering as a model of the of and basis of comparison of a real processes. So let's proceed further. Now, ideal gas relationships where P is the gas pressure in the cylinder, capital V is the volume in cylinder, small v is specific volume of a gas, R gas constant of air, T the temperature, M the mass of gas in cylinder, rho the density, H specific enthalpy, U specific internal energy, Cp and Cv is specific heat at constant pressure and constant volume. K is the specific heat constant that is equal to Cp over Cv, specific heat at constant pressure divided by specific heat at constant volume. Small w, specific work. C is the speed of sound. Now C, the ideal gas relationships. P into small v is equal to RT, where P is pressure, V is your specific volume, R is universal gas constant, and T is temperature. Now, PVP here, V capital V is the volume and M small is the mass of the gas in the cylinder. So we can write P is equal to rho RT, or another equation in terms of enthalpy. Derivative of enthalpy is equal to specific heat at constant pressure and differential of temperature. Differential of specific internal energy is equal to specific heat at constant volume, differential of temperature. Now, for isentropic process, we have P into specific volume raised to power K is constant. For in terms of temperature, specific volume K minus 1 constant, then T temperature and pressure 1 minus K over K is equal to constant. Work, specific work from 1 to 2 is equal to pressure at 2 specific volume at 0.2 minus pressure at specific volume at 0.1 specific volume at 0.1 divided by 1 minus K. Isentropic work in a closed system is equal to R T2 minus T1 divided by 1 minus K. And speed of sound is equal to 100 square K RT. Now, air properties value. Specific heat of air can be treated as a function of temperature, but for simplification, specific heats of air can be treated as constant due to a little variation in its value even in large temperature difference range. Different values of Cp and Cv used for operating cycles, leak exhaust flow and inlet flow at the lower temperature or end of a cycle during intake and the start of the compression, a value of K Cp over Cv is 1.4 is correct. However, at the end of the combustion, when the temperature has risen and pressure is also have risen, we take the value of K is equal to 1.3. That would be more accurate. Now, on your right side in green figure, this is the actual indicator diagram, PV indicator diagram of a four-stroke SI engine, which we have talked a little bit on in chapter 2. On your left in the blue shade, you have this ideal air standard Otto cycle. We will study this in detail. Okay, Otto cycle. The intake stroke of an Otto cycle starts with the piston at TTC and is at constant pressure process at an inlet pressure of 1 atmosphere. Let's see. You have on x-axis, this is volume. On y-axis, you have a pressure. Here we have TDC, and here we have BDC. Volume at TDC, volume at BDC. Here we have atmospheric pressure P naught. Piston is at TDC. It starts from here and it goes to at point 1. From 6 to 1 is your intake stroke at constant atmospheric pressure. So the intake stroke of an Otto cycle starts with the piston at TDC and is a constant pressure process at an inlet pressure of 1 atmosphere. This is good approximation to the inlet process of a real engine at wide open throttle. Remember this thing? This figure is of wide open throttle. We have three conditions: wide open throttle, partially open throttle, and when we have a supercharged or turbocharged engine. So now we are talking about ideal air standard Otto cycle with wide open throttle condition. So this is good approximation to the inlet process of a real engine at wide open throttle, which will actually be at pressure slightly less than atmospheric due to pressure losses in the inlet flow. Okay. The temperature of the air during the inlet stroke is increased as the air passes through the hot intake manifold. The temperature at point 1 will generally be on the order of 25 degree to 35 degrees Celsius hotter than the surrounding air temperature. If we suppose the atmospheric condition, the temperature is 25 degrees Celsius. When it reaches to point 1, here the atmospheric condition, the temperature is 25 degrees Celsius. When it reaches from the intake manifold to the combustion chamber into the cylinder at point 1, its temperature has risen in the range of 25 degree to 35 degree Celsius. So then the surrounding at air temperature. Now, the thermodynamic analysis of Otto cycle at wide open throttle. Process 6 to 1, we have a constant pressure intake of air at P naught. Constant pressure of intake of air at P naught. Intake valve open, exhaust valve closed. So there are two conditions here. We have a constant pressure intake of air at P naught, and the valve condition is inlet valve is open, exhaust valve is closed. So pressure P1 is equal to P6, that is equal to P naught. But in actual P1 here, the pressure will increase in the range from 25 to 35. But for ideal Otto cycle, we take is at constant. P1 is equal to P6 and P naught. So the specific work done from point 6 to 1 is P naught V1 minus V6. So volume at specific volume at BTC minus specific volume at TDC. So this is your work done at in process 6 to 1. Now the second stroke of the cycle in the compression stroke, which in the Otto cycle is an isentropic compression from BTC to TDC. Now see this figure. In this figure, piston is moving from point 1 BTC to TDC point 2. So this is your compression stroke. Okay. This is a good approximation to compression in a real engine, except for the very beginning and and the very end of the stroke, because at the very beginning and at the very end of the stroke, the things are different in a real cycle. In real engine, the beginning of a stroke is affected by the intake valve not being fully closed until slightly after BDC. So in real cycle, real engine, at the beginning of the compression stroke, the inlet valve is not fully closed. It closes after BDC, and at the end of the compression is affected by firing of the spark plug before TDC. So here, ideally speaking, your intake valve is closed, but in real, when piston starts moving here after BDC, somewhere here in this location, your intake valve closes. And at the end of the exhaust compression stroke, somewhere here, you have the ignitions. Okay. And then start the combustion. So your spark plugs, because of the firing of the spark plug, you have the ignition and then you have the compression. Also, there is an increase in the pressure during the compression stroke, but the temperature within the cylinder is increased substantially due to the compressive heating. You see, you are now going from BTC to TDC, pressure is increasing and temperature is increasing manifold due to compressive heating. So process 1 to 2 is isentropic compression stroke. Condition of the valve is all valves are closed. So the temperature T2 is equal to T1 minus specific volume at V1 divided by V2 raised to power K minus 1. So in terms of pressure, we get this equation. So the specific work done, P2 specific volume at V2 minus pressure at 1, specific volume at 1 divided by 1 minus K. So this equation comes in specific internal heat U1 minus U2, or we can write it CV T1 minus T2. Now, the next stroke is the compression stroke, is followed by a constant volume heat input process from 2 to 3. Now, here from 2 to 3 is a constant volume heat input. Combustion is going on from 2 to 3. So compression stroke is followed by a constant volume heat input process 2 to 3 at TTC. This replaces the combustion process of the real engine cycle, which occurs at close to the constant volume condition. In a real engine, combustion is started slightly before TDC, reaches its maximum speed near the TDC, and is terminated a little after TDC. It's in a real cycle. Okay. During combustion or heat input, a large amount of heat energy is added to the air within the cylinder. This energy raises the temperature of the air to a very high values, giving a peak cycle temperature at point 3. So at point 3, we have a peak temperature value, we have a peak pressure value. This increase in temperature during a closed constant volume process results in a large pressure rise also. Thus, peak cycle pressure is also reached at point C, as I already explained. At point 3, you have both peak temperature and peak pressure. Now the process 2 to 3 is constant volume heat input. The combustion process and the condition of the valve is all valves are closed. So the specific volume at point 2 and 3 is equal, and that is the volume, specific volume at top dead center. So the work done from 2 to 3 is 0, but there is a heat addition. So we can write it Q in, Q2 to 3, Q in, mass flow rate, mass of a fuel, heating value of a fuel, and the combustion value of a fuel, combustion efficiency of that fuel. So we can write mass of a mixture CV T3 minus T2. Mass of mixture is mass of air plus mass of fuel, CV T3 minus T2. So we can equate these equation and we can found these equation. T3 is equal to T max and P3 is equal to T max. Now we have a combustion. The very high pressure and enthalpy values within the system at top dead center generates the power stroke or the expansion stroke, which follows the combustion process 3 to 4. Now, here we have peak values. Now piston starts moving back towards BDC. This is your power stroke or expansion stroke. High pressure on the piston faces forces the piston back towards the BDC and produces the work and the power output of the engine. This power stroke of a real engine cycle is approximated with an isentropic process in the Otto cycle. This is a good approximation subject to the same argument as the compression stroke on being frictionless and adiabatic. In real engine, the beginning of a power stroke is affected by the last part of the combustion process because the end of the power stroke is affected by the exhaust valve being opened before BDC. So start of the power stroke is affected by the combustion, and end of the power stroke is also affected by the opening of the exhaust valve before BDC. During the power stroke, values of both the temperature and pressure within the cylinder decreases as the volume increases from TDC to BDC. At point 3, we have maximum temperature, we have maximum pressure. As the piston starts moving towards BDC, volume increases, pressure is dropping, temperature is dropping. Okay. A large amount of exhaust gases is expelled from the cylinder. Near the end of the power stroke of a real engine cycle, the exhaust valve is open and the exhaust cylinder experiences exhaust blowdown process. Okay. So in exhaust blowdown process, as we already know, a large amount of exhaust gases is expelled from the cylinder, reducing the pressure to that of the exhaust manifold. The exhaust valve is open before BDC to allow for an infinite time of a blowdown to occur. This is very important, that the exhaust valve has to be open before BDC for a finite time. It's because the high temperature and high pressure has to be removed from the cylinder. It is desirable for a blowdown to be completed by BDC so that there is no high pressure in the cylinder to resist the piston in following exhaust stroke. Now the piston has reached BDC. If we do not open the exhaust valve before BDC, there will be a large amount of pressure forces acting on the piston top. So the rearward moment in the exhaust stroke would be difficult. So that's why we open the exhaust valve before BDC to drop the pressure or forces exerting on the piston face so that the exhaust stroke starts smoothly. Now, the process from 3 to 4 is isentropic power or expansion stroke. Condition of the valves all valves are closed in an so Q3 to Q4 is 0. So work done is specific work done you can get from these equations. No, blow down in a real engine is therefore almost but not quite constant volume because the piston is still moving towards BDC. But in Otto cycle, we take it as at constant volume. A large quantity of enthalpy is carried away with the exhaust gases, limiting the thermal efficiency of the engine. So this is a demerit, but it has to be there. The Otto cycle replaces the exhaust blowdown open system process of a real cycle with a constant volume pressure reduction closed system process 4 to 5. Let's see. Now, this process 4 to 5 is your exhaust blowdown. Enthalpy losses during this process is replaced with heat rejection in the engine analysis. So it is Q out. First, we have process 2 to 3, we have Q in. Now, process 4 to 5, that is Q out. Pressure within the cylinder at the end of the exhaust blowdown has been reduced to about 1 atmosphere and the temperature has been substantially reduced by expansion cooling. Okay, temperature will be still high, but the pressure we have managed to reduce till 1 atmospheric. Now, process 4 to 5, constant volume heat rejection, exhaust blowdown, this process 4 to 5. Valve condition, exhaust valve open, intake valve closed. So we get these equations. Now, after the exhaust blowdown, the last stroke of the 4-stroke cycle now occurs as the pistons travel from BDC to TDC. Process 5 to 6 is the exhaust stroke that occurs at constant pressure of 1 atmosphere due to the open exhaust valve. This is good approximation to the real exhaust stroke, which occurs at pressure slightly higher than the surrounding pressure due to small pressure drop across the exhaust valve and in the exhaust system. Now, piston is at BDC and it starts moving towards TDC from 5 to 6. We have a exhaust constant pressure exhaust stroke at P naught, at 1 atmospheric. Valve condition is exhaust valve open and intake valve closed. So P naught is equal to P5, P6. So work done is like this. So the thermal efficiency of the Otto cycle is specific work net divided by Q in, or we can write it as 1 minus Q out divided by Q in. So in terms of temperature, we get 1 minus T4 minus T1, T3 minus T2. So thermal efficiency is of an Otto cycle is written like this in terms of temperature or in terms of specific work and heat addition. At the end of the exhaust stroke, the engine has experienced 2 revolutions. The piston is again at TDC, the exhaust valve closes, the intake valves open, and the new cycles begin. So again, the same repetition and same processes. So the thermodynamic analysis of the Otto cycle, we have this thermal efficiency of an Otto cycle in terms of temperature, or we simplify it 1 minus T1 over T2, or we can write it 1 minus 1 over RC. RC is your compression ratio raised to power K minus 1. Okay, K is the specific heat constant. Now, on the left side, you have a pressure volume diagram of a Otto cycle, and on the right side in green shade, you have temperature entropy diagram. At point 1, you have a less entropy. Point 1 to 2 is your, remember, the compression stroke. In compression stroke, your pressure is increasing, your temperature is increasing. So from point 1 to 2, entropy remains the same, but temperature is increasing. Now at 2, you are having ignition and combustion. Okay, so the temperature and pressure is rising to the peak value. So your temperature and pressure is rising to the peak value, and your entropy is also increasing. Now, from 3 to 4, you have power stroke. Pressure is dropping, temperature is dropping. Okay, but here entropy remains the same. Your temperature is dropping, pressure is dropping, but the entropy remains the same. At 4 to 1 or 4 to 5, you have exhaust blowdown. So you, temperature is dropping and pressure is dropping, and your entropy is also dropping. So this is your temperature entropy diagram of a same pressure volume diagram of a Otto cycle. Now, in terms of thermodynamics, from 0 to 1, you have an intake stroke. From 1 to 2, you have a compression stroke, that is isentropic process. Then you have a heat addition here from 2 to 3. Then you have a power stroke, that is isentropic process from 3 to 4. Then you have 4 to 1, you have exhaust blowdown, that is the heat rejection. And from 1 to 0, you have a exhaust stroke. And in terms of temperature entropy, 1 to 2, your temperature is rising. From 2 to 3 is constant volume, and 4 to 1 is your at constant volume. Now, real air fuel engine cycle. In real engines operates on an open cycle with changing composition. So there is a difference between standard Otto cycle and real engine cycle. Air standard analysis treats the fluid flow through the entire engine as air and approximate airs as an ideal gas. But at every instance, the pressure is changing, the temperature is changing, the composition is changing. There are heat losses during the cycle of a real engine, which are neglected in the air standard analysis. Combustions require a short but finite time to occur. So combustion requires a short but finite time to occur, and heat addition is not instantaneous at TDC as approximated in an Otto cycle. So these are the few comparison points. The blowdown process requires a finite real time and a finite cycle time, and does not occur at constant volume as in the air standards analysis. With ignition occurring before TDC, temperature and pressure rise before combustion is less than predicted by the air standard analysis. And the valve overlap period causes a deviation from the ideal cycle. So these are the comparison points, that how your real air fuel engine cycle differs from air standard Otto cycles. Now, the second condition, when we have a condition of pot throttle. First, we have seen wide open throttle. Now, this is when you have a pot throttle. Pot throttle means you have not pressed the accelerator fully. In first condition, previously, that was wide open throttle, means you have pressed the accelerator pedal fully, and your carburetor butterfly valve or other engine, you have a wide opening for the air. But here you are not fully pressing the accelerator pedal, or you are not fully engaging the mechanism. So it's a part open throttle. Okay. So when we have a part open throttle, so the intake is like this, from 6 to 6A and 1, quite below the atmospheric pressure. Then from 1 to 2, we have the compression stroke. And then 2 to 3, we have this rise in temperature and pressure, but it is less as compared to the wide open throttle. Then from 3 to 4, we have a power stroke, and then 4 to 5, we have an exhaust blowdown, and then from 5 to 6, we at atmospheric pressure, we have a exhaust stroke. Now let's see. A four-stroke cycle SI engine running at less than wide open throttle conditions means part open throttle. Air fuel input is reduced by partially closing the throttle butterfly valve in the intake system, creating a flow restriction and consequent pressure drop in the incoming air. Fuel input is then also reduced to match the reduction of the air because we have to maintain that air fuel ratio. So if you are reducing the air, the fuel input will also be reduced. Air experiences an expansion cooling because of the pressure drop across the throttle valve, but its temperature is about the same as the wide open throttle because it first flows through the hot intake manifold. So pressure will be slightly less as compared to wide open throttle, but the temperature will be almost the same as of wide open throttle. Now, the net indicated work for the Otto cycle engine will be less at part throttle than at wide open throttle because of these curves. Okay. The upper loop of the cycle made up of a compression and a power stroke represent positive or work output, while the lower loop consisting of the exhaust and the intake stroke is negative work absorbed of the rotating crankshaft. The two main factors contribute to the reduced net work at part throttle operation. The lower pressure at the start of the compression results in a lower pressure throughout the rest of the cycle except for the exhaust stroke, lowering mean effective pressure and net work. Now, when less air is ingested into the cylinder during the intake, because of this lower pressure, fuel input by the injector or carburetor is also proportionally reduced, resulting in a less thermal energy from combustion in the cylinder and thus resulting less work output. Okay. It should be noted that Q in is reduced. The temperature rise in process 2 to 3 for wide open throttle and part open throttle is almost the same, but the Q in is reduced. This is because the mass of the fuel and the mass of the air being heated are both reduced by an equal proportion. Now, work done during the intake stroke from 6 to 6A and 1. PI, the volume at 1 minus volume at 6. Work done during the exhaust stroke from 5 to 6. P exhaust V6 minus V5. So minus PX exhaust VD. Net indicated per pumping work. Work pump net PI minus P exhaust, P inlet minus P exhaust into displacement volume. Pump mean effective pressure. W pump net divided by VD is equal to P inlet minus P exhaust. Now, the third condition when we have an engine with turbo or supercharger. In previous, when we have a part open throttle, everything was happening here below atmospheric. Now, when we have a supercharger or turbocharger, higher intake pressure than the atmospheric pressure, more air and fuel in the combustion chamber, increased net indicated work. So we have a P naught here at 0.6, intake stroke 6A and then goes to 1. Your intake strokes completes from 1 to 2. We have a compression stroke from 2 to 3. We have a heat addition or combustion from 3 to 4. We have a power stroke from 4 to 5. We have exhaust blowdown, and from 5 to 6, we have exhaust stroke. Now, higher intake pressure increases all pressures through the cycle, and increase air and fuel gives greater Q in the process 2, 3. So when initially you are having high pressure, so all the pressure values will rise. Okay. When air is compressed to a higher pressure by a supercharger or turbocharger, the temperature is also increased. When we are compressing the air and sending into the combustion chamber, the cylinder, so its pressure is increased due to the compression, and in same wise, its temperature is also increased due to the compressive heating. This would increase air temperature at the start of the compression stroke, which in turn raises all temperature in the remaining cycle. So the pressure increases from at the start, so it's all the pressure values will be high. Similar goes for the temperature. The temperature at the start is high, so the temperature values will be high. This can cause self-ignition and knocking problem in the later part of compression or during combustion. But this high value of pressure and temperature will leads to a phenomena of self-ignition, and that is known as a knocking problem in the compression or during combustion. We will study in detail when we study the fuel. For this reason, engine compressors can be equipped with an aftercooler to again lower the compressed air incoming air temperature. So engine with having a supercharger can be equipped with an aftercooler to lower its temperature. Aftercooler are heat exchanger which often use outside air as the cooling fluid. Okay, so in principle, aftercooler are desirable, but cost and space limitation often make them impractical on automobile engine. It is a requirement, but due to space constraint and cost problem, we are unable to have this aftercooler in many of the vehicles having a supercharger. Instead, engine equipped with supercharger or turbocharger will usually have a lower compression ratio to reduce the knocking problem. So in order to cater for this knocking problem, because self-ignition of an air fuel mixture, so we use lower compression ratio. Okay. Now, coming to this previous lecture was of SI engine with wide open throttle, partially open throttle engine with supercharger or turbocharger, and ideal air standard cycle, Otto cycle, and rear cycle. Now coming towards the diesel cycle. Early compression ignition engines injected fuel into the combustion chamber very late in the compression stroke. Due to ignition delay and the finite time required to inject the fuel, combustion lasted into the expansion stroke. This kept the pressure at peak levels well past TDC. Remember this thing. In previous CI engine, the combustion chamber fuel is injected very late into the combustion chamber, nearly at the end of the compression stroke. Due to the ignition delay and the finite time required to inject the fuel, combustion lasted into the expansion stroke, the power stroke. This kept the pressure at peak level well past after TDC. This combustion process is best approximated as a constant pressure heat input in an air standard cycle. Now, the rest of the cycle is similar to the air standard Otto cycle. The diesel cycle is sometimes called constant pressure cycle, as the air standard Otto cycle is known as constant volume cycle, but for the diesel, it is also diesel cycle is known as constant pressure cycle. The difference between the Otto and the diesel cycle is method of heat addition. Here is the difference in this portion. This is the portion where it is the difference. Rest process is same. We have intake process, then we have compression process, then we have heat addition process here, combustion at constant pressure. Then we have a power stroke up to 4 here, and then we have this exhaust blow down. This is your heat rejection, and then we have then exhaust stroke. So in temperature entropy diagram, we have this constant pressure and we have this constant volume. Now the actual indicator diagram of an historic diesel engine is like this. It is somewhat different here as compared to your SI engine. Now the PV diagram and temperature entropy diagram. Briefly, I explained to you. P naught piston is at TDC, going towards VDC at point 1. This is your intake stroke. We are talking about ideal diesel cycle, okay, not real. So at constant pressure, we are having a intake stroke. From 1 to 2 is your compression stroke. Somewhere here you get the combustion and you inject the fuel and then you have the self-ignition. At constant pressure, but the temperature will be high here. Then heat addition. Then from 3 to 4, you have the power stroke or the expansion stroke. From 4 to 5, you have the exhaust blow down. And then 5 to 6, you have the exhaust stroke. Now, from 1 to 2, you have a compression stroke. Temperature is rising, pressure is rising. Then from 2 to 3, you have a combustion. So peak values are obtaining at point 3. Pressure is still rising, temperature is rising. 3 to 4, you have a power stroke. But remember this 4 temperature at the end of the power stroke is still higher than the temperature at the end of the compression stroke. Remember this thing. Temperature at the end of the power stroke is still higher. See, temperature at point 4 will be still higher than temperature at point 2. Point 2 is the end of the compression stroke and point 4 is end of the power stroke. Okay, so remember this thing. Then from 4 to 1, we have exhaust blowdown. Okay, now let's see the thermodynamic analysis of air standard diesel cycle. Cost pressure 6 to 1, constant pressure intake of air at P naught, valve conditions, intake valves open, exhaust valve closed. Okay, so the specific work done from 6 to 1, P naught V1 minus V6. Now, process 1 to 2 is isentropic compression stroke, valve conditions, all valve closed. So we get the temperature, volume, and pressure volume equations. So the work done will be like this. Now, process 2 to 3, constant pressure, heat input combustion. Here, 2 to 3, constant pressure, heat input, valve condition, all valve closed. So Q in, mass of fuel, heating value of fuel, combustion efficiency of the fuel. So we get these equations. So T3 is T max. Now, another term here, cutoff ratio is defined as the change in the volume that occurs during combustion as a ratio. Point 2 at TDC, but the combustion is finished here. Okay, heat input. So at that point, the volume is different. So the cutoff ratio is defined as the change in volume that occurs during combustion as a ratio. And the cutoff ratio is defined as beta. So we V3 divided by V2 or specific volume at V3 divided by V2 is equal to T3 divided by T2. So cutoff ratio in terms of volume or specific volume with respect to the temperature. Now process 3 to 4, from 3 to 4, isentropic power or expansion stroke. Valve conditions, all valve closed. So in terms of temperature and specific volume, we will get these equations, pressure and volumes. And in terms of work, we get these equations. Now process 4 to 5, constant volume heat rejection is exhaust blowdown. Exhaust valve open and intake valve closed. So this is the valve condition. So Q out will be in these equations. Now process 5 to 6. This one from process 5 to 6. Constant pressure exhaust stroke at P naught. Constant pressure P naught, exhaust value valve open, intake valve closed. So work, specific work done from 5 to 6, P naught V6 minus V5. So P naught V6 minus V1, specific volume. The thermal efficiency of a diesel cycle, the thermal efficiency of a diesel cycle, we can write work net divided by Q in. So 1 minus Q out over Q in. So 1 minus CV T4 minus T1 divided by Cp, because it's a constant pressure. So T3 minus T2. So Cv over Cp is we know K. With rearrangement, this can be shown to equal thermal efficiency of a diesel cycle is 1 minus 1 over Rc, K is minus 1, bracket beta raised to power K minus 1, bracket closed, divided by K beta minus 1, where Rc is the compression ratio, K is the unit specific heat constant, Cp over Cv, and beta is the cutoff ratio. Now, dual cycle. Previously, we have studied diesel cycle, now dual cycle, in which we combine both the constant volume and constant pressure cycle. In Otto cycle, combustion is assumed to be at constant volume, and in diesel cycle, it is at constant pressure. So in Otto cycle, the combustion is at constant volume, and in diesel cycle, it is at constant pressure. This is far from real, as some time interval is required for the chemical reaction during combustion. So this is far from real. Remember this thing. The dual cycle, also called mixed cycle, is a compromise between Otto and a diesel cycle. In a dual cycle, part of heat is supplied at constant volume and then at constant pressure. So the PV diagram will be look like this. You have same intake process, then you have same isentropic compression. Part of heat addition is at constant volume, part of heat addition is at constant pressure. Then we have an expansion stroke, the isentropic process from 4 to 5, the power stroke, then from 5 to 1, we have exhaust blowdown, and this is at heat rejection. And then 1 to 6, we have a exhaust stroke. So in T temperature entropy diagram, 1 to 2, we have the compression stroke. From 2 to 3, we have heat addition at constant volume. And from 3 to 4, we have a heat addition at constant pressure. Then 4 to 5 is your power stroke. Okay. And from 5 to 1, we have the exhaust blowdown. So the actual diagram will be look like this. The PV from P naught 6 to 1, we have the intake stroke. 1 to 2 is your compression stroke. 2 to X is your constant volume heat addition. From X to 3 is constant pressure heat addition. 3 to 4 is your expansion stroke, isentropic process. And 4 to 5 is your exhaust blowdown, constant volume heat rejection. And from 5 to 6, you have the exhaust stroke. Same here. In thermodynamic analysis of the air standard dual cycle, from process 2 to X constant volume heat input, first part of the combustion, wall conditions, all wall closed. Vx is equal to V2 is equal to VTDC. So we get these equations. The analysis of the air standard dual cycle is the same as that of diesel cycle, except for the heat input process combustion 2 to X and X to 3. Now the pressure ratio. We in diesel cycle we have the cutoff ratio. Now in dual cycle we have pressure ratio. Is defined as the rise in pressure during the combustion. Alpha, we denote it as alpha. Px, pressure at Px divided by pressure at P2 is equal to P3 divided by P2, P3 divided by P2 in terms of temperature. Tx divided by T2 is equal to 1 over Rc raised power k P3 over P1. Now, the process from X to 3, the constant pressure heat input, second part of the combustion, wall condition, all wall closed. P3 is equal to Px, P max. So we get the specific work equations and Q equation like this. Now the cutoff ratio, beta is equal to V3 over Vx, V3 over V2, V3 over V2, and T3 over Tx. So we get these equations. Now the thermal efficiency of a dual cycle. Thermal efficiency of a dual cycle, specific work net divided by Q in, 1 minus Q out over Q in, that is 1 minus CV T4 minus T1, or divided by CV Tx minus T2 plus Cp T3 minus Tx. So we get the equation after simplification, 1 minus T4 by T4 minus T1 divided by Tx minus T2 plus K T3 minus Tx. This can be rearranged to give the thermal efficiency of a dual cycle. 1 minus bracket 1 over Rc, K minus 1, bracket alpha. Alpha is your pressure ratio, beta is your cutoff ratio, raised power K minus 1. Then divided by K, K is your specific heat constant, alpha is your pressure ratio, bracket beta is your cutoff ratio, minus 1 plus bracket close plus alpha, the pressure ratio minus 1. So this is the thermal efficiency of a dual cycle. With this, we end today's lecture and we will continue further in our second lecture.